is how we roll, man. Some rock, some win, some 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 roll.
Hi, my name is Loris Crow, and we are executing at Showtime. Zig Showtime is the show where members of the Zig community come on stream to share coded ideas with the broader public. Every episode features two speakers who will present and take questions from you, the viewers. Zig Showtime is not just what you're seeing on the live stream, but also the discussions that you can have while watching. And that's why I encourage you to join one of the existing Zig communities that you can find by going to ziggen.org. Today's episode features two interesting sessions, starting from Benjamin Feng, who will talk about what memory allocators are and why they're needed. And after Benjamin, Andrew Kelley will talk about the Zig compiler internals. Before we begin, I have a few announcements about the next episode of Zig Showtime. So, first of all, the next episode is going to be the last episode of this summer. The show will resume in September, meaning that we will be on a break for the second half of July and all of August. There are two reasons for this break. One is that I will be able to get some time back and invest it into improvements and, I don't know, maybe take a short vacation, who knows. The second reason is that right now I'm almost out of applications and I hope to get some more by September. As you know, the show can't exist without speakers, and we've had a good run actually, right? We are right now at the 5th episode without interruptions. Every episode, two very nice talks, both from regulars of the community and also from people joining from other communities, and that was awesome. And also, I mean, it's what Europeans do, right? Disappear during summer. So the second announcement is that the next episode is going to air at a time that for once is Australia friendly. So it will air at 3 p.m. Pacific time, so 6 p.m. Eastern time, midnight in Central Europe, and 8 a.m. Sydney time. So I'm looking forward to having Eleanor and Dorminator present in chat, and of course other Australians too. The third announcement is about the date. So to prepare the next episode, we'll need more time. And so Zig Showtime number 6 will air on July 11th. So that's 2 weekends from now, right? We are skipping 1 weekend. Coincidentally, this will also allow our fellow American viewers to enjoy their 4th of July celebrations and, I don't know, be hungover on the 5th. I don't know what people do there. So why do we need more time? Well, because it's going to be a special episode. Zig Showtime number 6. For Zig Showtime number 6, there are no speaker announcements. It's going to be, as I said, a very special episode, more interactive, and with a few surprises. I assure you, if you can make it, you will want to be there. But we'll share some more info near the end of today's show. So now I think it's time to introduce the first speaker, I guess. So let's switch view. Benjamin Feng is not only our first speaker today, but also our first returning speaker ever. Normally I try to make a joke in the introduction, but this time all I want to say is thank you, Benjamin, for your courage and your effort. His talk today is the first talk that we are hosting meant to introduce newcomers to the Zig programming language to a systems programming concept. The title is What's a Memory Allocator Anyway? And Benjamin, the stream is yours.
Hi, thanks for the introduction, Loris, and it's good to be back. And let's get started with our talk. So as Loris has just mentioned, my talk is going to be on memory allocators, specifically manual memory allocation. And to understand what is a memory allocator, we need to understand why is a memory allocator. And that's actually a pretty good question because let's take a look at what the Zig compiler will provide for us. So this is just a very simple function that I wrote up real quick. All it does is it takes two variables, a start and an end, and it goes and it sums up everything in the middle. And how that looks in the actual compiler is that we will be provided a segment of memory. At the very top is going to be some function metadata, specifically the return address, but it may include some other things in there. And then we have the two variables that we're passing in. Let's pretend that this is a very dumb compiler and we're not using registers. So we're going to reserve start and end as part of the memory that we need in our execution. And then we also need the result and the current. And the result is the data that we return back, and the current is sort of a temporary space. And this is all the memory that we need for running this function. Every time you invoke this function, it will go. The compiler will go ahead and just reserve all this space for you. And the nice thing about this is you don't have to think about it. As a general programmer, I never have to really think about any of this stuff because it's all automatic. Like stack memory is handled by the compiler and it's handled really well because it has very simple semantics. And you know exactly what's going to happen. It's very fast at allocating because you literally just advance a pointer a couple of steps so that you have enough memory. And you also have, because everything is predetermined by the compiler will literally just write a bunch of offsets in the middle of your code. It doesn't have to calculate any of that. It's just purely based on what's in the stack right now. So everything is fast, and cleanup is just the opposite. You just unwind a single pointer. So everything's fast, and everything is basically trivial to the compiler. So why isn't this good enough for all programs? Why do we need a concept of manual memory allocation? Like there are some fundamental limitations on how you can use the stack. And the first big problem is you have a fixed amount of total memory. And this, depending on which operating system you run, this may be a little bit more flexible into how much fixed total memory you have. But generally speaking, you're never going to be able to allocate gigabytes on the stack. That's just something that the operating system will not allow you to do for pretty good reasons. So even if you are able to expand the stack, you're still having a limit as to this is not the total memory. If you want 16 gigabytes, you need some other way of accessing that memory. You also have a problem with fixed sizes because the compiler needs to know exactly how big the memory space is for every variable in your program. And so they must be fixed. And if you need any sort of dynamic allocation, for instance, if you don't know the size of something or you need to like expand the size at some point, this is not really possible on a stack. I mean, it's a little bit possible in some operating system, like Linux gets you allocate, which allows you to expand stack variables. Zig actually doesn't let you do that because it was found to be unsound and buggy. So we can't actually do that in Zig, and we don't want to do that in Zig. A workaround here is you can allocate a maximum buffer size, and that way you can sort of have a maximum size that you can allocate towards. But if that maximum size is not big enough to handle, say, user inputs, then your program can't actually operate on that. And the last problem is lifetimes. Because of the way that the stack is structured, the lifetime of this variable only exists inside this function call, or in Zig, it's actually inside of a specific block. And that's kind of that's not a problem if you're using values directly. So if you're always copying around the start value, the end value, that's not a problem because you're just passing around values. As soon as you use pointers, pointers into stack memory can easily be hanging references. And that's the same type of bug as a use after free bug. And that leads to memory corruption and all sorts of really bad things. Because you don't have control over your lifetime, you can't build something like a linked list on a stack and return it. So these are all sort of very big limitations with how the compiler works with memory. And it's, in general, you want to use stack memory as much as possible. But if you run into these limitations, you can't really leverage the stack anymore. So what do? Well, let's come up with the simplest allocation strategy. The easiest way to do manual memory allocation is by making someone else do it. So like the operating system gives us a way to ask for more memory, and we'll just see what that looks like. And this is sort of a dumbed down version of the page allocator that exists in the Zig standard library. It's a bit more complicated than that, but this is sort of the meat that I want to focus on. And in an allocation, what we do is we'll just go ahead and request the memory from the operating system, and in a POSIX system, that's memory map or mmap. And upon freeing it, we just call memory unmapped. And this is very simple and almost trivial. And you might be wondering, hey, what's the catch? Well, like, why can't we use this? Why is this not actually recommended by Zig? And there's sort of a problem going on with this. And for one thing, system calls are very slow, like in orders of magnitude slower than a typical function execution even. And this is because of a number of things that have to relating with memory protection and interrupts and jumping into kernel space. All that stuff is very slow to execute, and it trashes how the CPU wants to view memory. So if you're doing many of these allocations, this is actually going to be a massive slow point in your program. If you're allocating, for instance, a dozen different nodes for your linked list, every time you ask the operating system for a node, it's going to be super slow, and it's not a good way of running things. And the other problem is that it is very wasteful. You may have seen this align forward and wondering what the hell is going on here. And that's because the operating system has a very stripped down view of memory. It does not understand memory in bytes, because if it was trying to figure out memory in bytes, it'd be very slow and wasteful. So the operating system actually has a view of memory in pages. And a page is typically 4 kilobytes for most modern operating systems, and it's 64 kilobytes on WebAssembly. And that means that whenever you ask for memory, you have to ask for a page or a multiple of a page. So if you're asking for 8 bytes for your linked list, well, you can't. You have to ask for 4 kilobytes. And then your linked list will use 4 kilobytes of that 8 bytes of that 4 kilobytes, and you're wasting 3.99 kilobytes every time you're asking for memory. So this is really bad in 2 different, very catastrophic ways. So now the flip side you may be asking is, if it's so bad, why do you want to use the operating system at all? And the answer is the operating system actually has all the memory that's available. When you run your program, you typically don't map all the memory that you need directly into your program immediately. So you need some way of asking the operating system for more memory. Now, you can start with all of the memory mapped, but that means that your memory usage is governed by how much maximum memory you have at all times. So if at a maximum you need 1 gigabyte of memory, you map 1 gigabyte when you start out, and that's not ideal, because if most of the time you only need like maybe 10 megabytes, then that extra memory is wasteful. It may not start up, and it's just all sorts of I can't think of the word. Not optimal, unoptimal. There we go. So that's why you want to ask the operating system for more memory. And this is sort of the basis of most of the allocators, but it's also not what most people use as allocators directly, because again, it could be very wasteful. So instead of just like trusting someone else, how about we actually implement one? This way we have a little bit more control of what's going on. So what is the simplest allocation that we can, or what is the simplest algorithm that we can do? And that's called a bump allocator. And it's in Zig, we provide a bump allocator in the form of a fixed buffer allocator. We use a fixed buffer to back a single allocator. And the allocator, all it does is it stores an extra field called the end index. And as you allocate, you bump the end index upwards, and you create these segments of memory at the bottom of the buffer, or at the top, depending on your strategy. But as you allocate more memory, you just bump the pointer upwards a bit. And that way, you actually track how much free space you have left. And also, you track how much memory you have previously consumed. So there are a number of downsides to this, but the big benefit is that this is very simple. It's very simple, and it's very fast. So because allocating memory is just a couple of additions, comparison, plus, and that's really it, you get very fast allocation. And you get a little bit more control over the lifetime. It's not fully controlled because depending on where you put the buffer, so your lifetime is now controlled by where your buffer lives as opposed to where your variable lives. And that gives it a little bit more flexibility. You can move the buffer from this current stack upwards into the stack. That gives it a bit longer lifetime, or you can even move it out to the global space. It's still not like complete control over where it is, but it's a lot better. So you won't accidentally like start pointing into accidentally pointing into free memory that's no longer part of the mapped stack. But there are still major problems with this. Probably the biggest problem that we have is that your memory is still fixed. We call it the fixed buffer allocator because your buffer is fixed. We can't expand it in any way. So once you run out of free space, then there's nothing you can do, and you just sort of hold your hand and be like, well, we're out of memory. And this is even worse because you can't actually free memory. Now, we can sort of wiggle our way around and say, oh, you can free memory. You can free the last allocated memory. It's like in this instance, we can free the 32 byte because it's at the last spot and we can detect that. But we can't actually free the 8 bytes at the very beginning or the 4 bytes in the middle. There's no data structure to store that because all we're storing is an end index. So free is very limited, and the only way to properly free is to do a first in, first out approach, which when you work with manual memory management, it's very hard to guarantee that. So in most respects, you could treat it as you can't free memory, and any free memory that you actually get is sort of an optimization and not an actual like something that you can depend on. So yeah, we can free the last allocation. But the other thing that we can do is we can reset the entire buffer. Because the allocation, because we're storing the end pointer, we can just be like, oh, the end pointer, let's point it at the beginning. So even though we can't really free individual memory, and trying to free it with the last allocation is brittle, we can actually reset the entirety. If we know that this the data that's inside this buffer is no longer being used, we can just go ahead and flush it and start from scratch. And that's actually very fast, and that's a valid way of reusing your buffer space. But so let's skip and let's ignore the fact that you can't really free memory right now, and let's talk about fixed total memory. Personally, this is kind of a bigger blocker for me because like there are often times I don't know how much memory I need. If I'm writing parsing code, I can just keep guessing until I get the right number of free memory, but that seems very not fun. So what can we do to lift this idea of a fixed total memory? Like, what if we could have a bump allocator with expandable memory? So instead of having one fixed buffer, how about we have expandable buffers? So here we just basically fill up individual buffers, and every time we fill up a buffer, we'll just go ahead and we'll create a new buffer. And if we fill that up, we'll create a new buffer. This way we have unlimited memory as long as we can create buffers. And we still have the bump allocator style where we're just moving up the pointer, and that's still going to be really fast. I may be asking, well, where are the buffers coming from? And the answer is this type of allocator requires a backing allocator. So something else needs to be providing the actual memory that's happening. And just so happens we just explored one of the allocators, and that's the operating system. So we'll have Tux here give us all our memory for us. And this way, we have the capability of having expandable memory while mitigating most of the downsides of hitting the operating system and asking for more memory. So for instance, if you start allocating a bunch of linked lists inside this new allocator, which we're going to call Arena Allocator, we're actually just going to be bumping up the memory here, and we very rarely will need to ask the operating system for more memory. So this is a lot more performant, and it sort of mixes two allocators together and gets the best characteristics of both. And again, it's very fast allocation because it's still bumping. You have expandable memory, which is good, and the other great thing is that you have fully controlled manual lifetimes. Previously, with our fixed buffer, we're still governed by where the buffer lives. But now, since we're actually asking the operating system for memory, we can control when that free happens. So whenever you're done with it, you can't free individual memory. That's still not allowed. But you can free all of the memory that we have requested, and that just goes directly back into the operating system. And not being able to free individual memory, that sounds like a sort of a limitation, and it is. But however, there are many types of problems that you can actually get away with not freeing individual memory. And the two big there are two big categories of algorithms that freeing individual memory may not be that great. The first one is if you have lots of allocations for one lifetime, freeing individual memory is not actually that useful. If you think if you've used malloc before in the past and you build a linked list and then you have to free that linked list, you have to go through and iterate through each individual node to figure out where to actually go and free it. So if you have like 100 nodes, you have to do 100 different freeing. You have to free 100 different nodes individually. It would be nice if we could free them all at once, and you can with an arena. You stick all of those nodes inside of a single arena. You put it at the top of the tree, or the list in this case, and then you can just go ahead and free all of them at once. And that's a much faster operation because you're not iterating through a bunch of nodes, and it's one operation because you have basically one chunk of memory to store all of that. The other and slightly more fuzzy approach is that if you don't have to free individual memory, if your lifetime is known and you can get away with a little bit of temporary garbage space, then you don't need to free individual memory and you still have the easy lifetime of the arena. So in this case, for instance, a web request, you can structure your arena in a way where you create the arena at the beginning of a request and you free the memory at the end of the request, and everything in between is automatically cleaned up for you. And this while it's not ideal because if your request actually allocates like megs of memory and then tries to free them, it's still going to be hanging around until the request is finished. But it also protects you from leaking memory outward in case you didn't free it. So this is, if you have a known lifetime, applying an arena can make your system a lot more resilient to like manual memory management holes that you may have forgotten. So this is actually a very popular strategy in Zig. We do it all the time, and the standard library does it for like parsing. It does it for other type of handling, and it's a surprisingly flexible strategy. However, there's still a problem with not being able to free memory. I'm not saying that it doesn't happen because it always does. So what do we do about freeing memory? Like, how do we make this memory allocation general purpose? And the easy solution is we just create some metadata and stick it in a free list. And how that works is looking at this code here. Let's skip ahead to the free algorithm. And instead of returning the memory anywhere, we're just going to create a linked list node out of the memory, and we'll append it to, or prepend it into our little free list tree here. And then whenever we need to allocate new memory, we can go ahead and we find a matching size. And this way, we are creating a linked list of these nodes, and each of these nodes can be of a different size, and then we can basically find it again if we need more. And if we can't find a matching size, that means, oh, we don't have the existing memory. We're going to have to actually go and create new memory. And this does work. You can free memory. You have some way of storing free memory, and that's really our goal, right? Well, there are major problems with this approach. And for the first thing is that allocations have a limited size. In order for us to free memory, we need to be able to store it in a linked list. So we need at least a next pointer. And a next pointer has a minimum size of 8 bytes on a typical 64-bit machine. And so whenever you allocate 1 byte, we have to bump that up to at least 8 bytes in order to free memory. Or we can just go ahead and never be able to free anything less than 8 bytes. There's a trade-off there, but the point is that we have some issues with that. This is also very slow. In order to allocate memory here, we all of a sudden converted this from a constant time to a linear time, because we're actually scanning through the entire list in order to find free memory. That's O of 1, and that's going to be slow. That's not ideal. It's possible for it to be the memory that you're looking for is in the front of the list, but there's no guarantees there. And there's also a problem with fragmentation. Now, this gets into other considerations, but like, say if you allocate 8 bytes, and then you allocate 1 byte, and then you allocate 7 bytes. Ignoring the fact that we can't really free those things, that 1 byte of allocation is actually segmenting your memory and preventing it from being used ideally. So if you free these chunks of memory, now you have an 8, 1, and 7 chunks, even though it could be 16 bytes. And that leads to horrible degradation of performance the longer your program is running. And there's no such thing as defragmenting your memory, because you have pointers that go everywhere and you can't really track them down. So this becomes a huge concern. And this is just, even though this works for like our general purpose, this is not ideal. And I almost don't want to use this because it's so bad. So how do we fix some of these problems? And so the answer is, what if we introduce a concept of size buckets? Now we have different lists for different sizes. And the big thing that happens here is that if you have a different if you have a different list for different size, the first access into that list is guaranteed to be the right size. So instead of traversing through the entire list of things, you only need to find one value. You only need to find the first value. If it exists in the list, then that's good. That's what you're looking for. If it doesn't exist, well, it's empty. You don't have to look through the entire list, and that's really good. And for fragmentation, it's a bit more mitigated. Let's put it that way. We no longer have a 1 byte chunk or 7 byte chunks or whatever. Everything's a fixed size. So for something like a 1 byte, we'll just bump it up to 8 bytes. For something like 10 bytes of requested memory, we'll bump it up to 16 bytes. And that way we have our nice limited trees, as well as reducing the contention of memory fragmentation. It's not completely gone, but it's a lot more mitigated, because like, I'm pretty sure that we can reuse 8 bytes or 16 bytes or 32 bytes. I have a hard time of thinking about reusing something like a 13 byte chunk. So we can definitely reuse these. It's just that it's still not ideal, because you still get some fragmentation. So it's not all gone. And then the limitation is allocations have a fixed size. That actually is a little bit of a problem, because now allocations, you can have wasted memory in allocations. If you're asking for 10 bytes and you get 16 bytes, that's 6 bytes wasted. That's not a lot at a small scale, but it can accrue up to pretty large numbers. So any other problems with this approach? And the answer is it's a little bit subtle, but the bigger problem here is we have cache pressure. And modern CPUs are very fast. They're so fast that they're like hundreds of times faster than memory. So whenever you run out of cache, you have a cache miss, then you have to actually access random memory, and that's really slow. And the way that we structure any sort of linked lists, you almost guarantee to run into cache problems. And that's because of the way that the linked lists are written, where your nodes can jump all over the place in memory. There's actually no structure whatsoever in the naive approach, and it's very hard to actually keep it structured. And when you're allocating single bits of memory at a time, this is not really a problem. I mean, it is a problem because you have cache pressure, but it's guaranteed to be a cache miss anyway if you're allocating sporadically. Like this data structure is not going to be in the cache. But if you're allocating very quickly, like say in a loop, you need to allocate 10 different free nodes, then every access to this node is going to be a cache miss. Can be a cache miss because it's jumping all over the place in memory, and that's really bad. There are ways to mitigate that by, instead of allocating 10 nodes by themselves, you can allocate 10 nodes at a time, and that's a strategy called object pooling, and that works really well. But that's outside of the allocation, outside of the allocator. What if we can do something to the allocator to make this type of behavior better? Because this is actually a pretty common use case. We don't want to always be like, oh, hey, you're using my allocator? Well, you should probably pool everything together. Because, yeah, you probably should, because it's a better approach by default. but a lot of people may not be thinking about this. And also, like, even if you are thinking about this, there are times where you don't necessarily know the total number that you want to pull in, and pulling together it may either give you too little, which is not which you need to expand memory, which is slow again, or you allocate too much, in which case you're taking up a lot more memory than you need. So is there anything that we can do to make our memory more cache friendly? And yes, we can, because we can actually, instead of using a linked list, we should be using arrays. Arrays are much faster and much friendlier to the CPU nowadays. And this gets into slab allocator. And a slab is sort of harkens back to our arena allocator, whereas we instead of having these buffers, they're now called slabs, and each slab is segmented in a way that the entire slab has the same amount of memory. And this has a very nice characteristic that linear memory, or amounts of memory that are allocated next to each other, have a much higher chance of being actually next to each other. So in our case, if we try to allocate four nodes from the first size, they're going to plug in right at the four bright areas, and two of them are literally right next to each other, and they're all very close by. And slab allocator will guarantee that whenever you allocate memory, it's going to be probably pretty close to each other. We can't guarantee that, because obviously we can't guarantee how the memory can be freed, but this has a much higher likelihood of being next to each other than using a linked list, because of the way the algorithm's structured. And also, we still have the fixed sizing, so that we can access different sizes pretty easily. And this actually fixes most of our problems with what we had before. Allocation still have the fixed size. That's sort of a problem. We're no longer very slow. We don't actually have traditional memory fragmentation anymore, because our memory will be fixed sizes. So there's no such thing as memory fragmentation in our case, because everything that's on the 8-byte slab will be guaranteed to be 8 bytes. You can't fragment that. And we got rid of a lot of the cache pressure. So this sounds like this is great. So what's the catch here? And there's a catch, and that's the meta storage. Depending on how you store the metadata, it can cause problems. And basically, if you want to store the metadata outside of the slabs, that's a possibility. But now you have an external set of memory that you need to manage, and that has its own characteristics. You can run out of external memory, and that would be really bad. And also, it's another external memory, which means it's another cache problem. If you put it internally inside the slab, that actually takes up a spot in your slab. So, like for instance, it takes up at least one element in your slab. So if you have if your slab is 1 kilobyte of blocks at a time, then your metadata will actually take up an entire kilobyte, even though you only need 10 bytes there. So that is not ideal, and that's pretty wasteful. So there are, again, more mitigation strategies, and that's probably going far beyond sort of the content that I can cover here. But there's actually a lot more going on that I sort of glossed over. So we have all these other ideas that we probably need to solve, because allocators need to sort of understand these things. Alignment's a big contention, especially with the modern day. A lot of things require memory alignment for things like SIMD and GPU work. If their memory is not aligned, you actually can't access it, and alignment requires its own little algorithm to calculate everything correctly. C compatibility, we don't actually care about a lot of that in Zig, because Zig allocate and free carries the metadata around. C, when you free memory in C, it doesn't actually, you don't pass the size back. So that size needs to be accessed somehow by the memory allocator. So that idea needs to, if you want malloc and free compatibility, you need to start worrying about additional ways of how to store your data. There's also like threading, everything that I've talked about, just ignore the concept of threads. If you, the naive way is using locks, but that's actually really slow. So a more modern way is that you actually have different affinity for memory. So different different threads will get different blocks of data. So like a slab will live only on one thread that's thread local at that point. Other ideas, memory efficiency, we talked about corruption. If you accidentally do a buffer overrun, do you write garbage into the middle of your memory, into your metadata, which is really bad? Or do you accidentally write to some data, which is a lot less bad, potentially? Or do you write to additional buffer, which is actually could be okay, that could be a way to work around buffer overruns by just allocating a lot more data. And there's also debugging and binary size. So there's a lot of these things that has to happen in any sort of allocators. And the point is that it is impossible to make an allocator to do everything well. And even though we call it a general purpose allocator, there's not actually one true general purpose allocator. That's why we have lots and lots of different algorithms. And I personally believe that Zig is in a great spot for allocation because of the way that we structured it. So there is no default allocator. We have to make decisions around all of these things. And that I believe that that's a good thing. And even if we get a general purpose allocator, which we don't right now because writing one is hard. But even if we do, I'm hoping that because allocation can be tricky and you can have different ideas of what you want out of your allocator, that we can still keep this idea of, okay, we're going to use an arena here, we can use general purpose here, we can use a different general purpose here because we need some debugging thing to do. And mixing and matching allocators in Zig is a lot easier than almost every other language. Like C has malloc, everyone uses malloc. That means you can't really swap out. And C++ has new and delete, and almost everything has a default. And because Zig doesn't have a default, I think it's in a better spot in terms of allowing you to manually manage all of this memory. And that's really the meat of what I have. I can be found sometimes streaming on Twitch. And I've written my own little general purpose allocator for WebAssembly. It is targeted towards WebAssembly, so I made the trade-offs of I don't care about threading, and I'm trying to squeeze it down as small as possible. And I am trying to convert it into a slab allocator, and I guess we'll see how well that goes. Thank you very much for having me on.
Thank you, Benjamin. Let's switch to the Q&A now then. Just a reminder to the people, to the viewers, to ask a question to Benjamin, remember to tag me in the chat message so that I don't miss it. You can send a message on Twitch chat, you can send a message on Discord, or also the Zig IRC channel on Freenode. So I'll be monitoring all these places. Let's switch to the Q&A now. Okay, so while people start thinking questions, if they have any, let's start with a few basic questions. So, how are you, Benjamin? How do you feel? This is your second talk, right? So, was it easier than the first time? Yeah, how do you feel in general?
I'm feeling okay. Definitely a little bit more nervous because this topic is something that I'm less familiar with. But yeah, I'm enjoying myself so far. I hope that everyone else is too.
Yeah, I've seen quite a few positive messages on Twitch, at least. So I think people appreciate it. And I remember before the show started, there were a few people like Timmy and somebody else that were interested in knowing more about allocators in Zig in particular, because as you pointed out, it's a bit of Zig is in a bit of a peculiar situation when it comes to allocators. So let's see a couple of questions that we have already. I'm curious about memory alignment. When using an allocator, do I need to care about memory alignment for a block of memory that I give to the user, or alignment of headers that the allocator use?
Yeah, so in Zig, I sort of had a dumbed down version of this method signature there, but we actually care about the alignment that the user is requesting. So the alignment of the headers and the metadata, it doesn't matter outside of your allocator. So you can put that anywhere you want to, provided that your allocator is able to access them. But for the consumer, they need the memory to be aligned. And so typically the limit in at least C land is 16-bit aligned or 16-byte aligned. Sorry. And that allows for 128-bit memory, which goes well into SIMD registers. But that's sort of the implicit alignment for malloc. For Zig, we actually pass around the requested alignment, and you have to match the requested alignment whenever you give back. The alternative approach is if you can't actually give alignment like that, you can just return out of memory. And that's a valid strategy. And now I would argue that your memory allocator is not quite general purpose, but maybe that's a good enough trade-off. And again, that speaks to how Zig works, that you're allowed to make these trade-offs. If you don't need any sort of special alignment, it's easier to do just standard 4-bit alignment. And if that's a disadvantage that you're comfortable with, you can actually write allocators like that. Whereas in C, malloc has to align to at least, I think, 16 bytes on a x86 system nowadays. Could be even higher now with AVX instructions, but like Zig gives us the flexibility of treating that alignment how you want to.
We have another question. Could we plug in something like oh, now that I think about it, I don't know how to pronounce the name. Jemalloc, Jemalloc.
Jemalloc?
Jemalloc.
Yeah. So in Zig, we actually have a way to expose a C allocator, and you just link a libc into it, and you can link any malloc compatible layer into Zig, and that'll work actually. That works quite well. The problem is that, again, C malloc is only 16-bit aligned. If you need more alignment, C malloc won't provide that for you. But if you need a general purpose allocator right now, the official approach is that, yeah, you can just link in whatever C allocator you want to, and it should just work.
Okay, so the solution that you're proposing is, so one way would be just to link against that by selecting the right library, but there was a second part of the question, so just to cover everything, it would still be possible to like create a Zig Jemalloc project on GitHub where you link the C library and provide your own like Zig Zig-like interface, right, to it.
Mm-hmm. Oh, you don't need to provide the Zig-like interface. That's actually the standard library provides a Zig-like interface on top of any C malloc. So okay. You don't need to write a special one for that. You just pull in, I think it's std.heap.c allocator, and it'll just work as long as you linked in a libc.
Perfect.
And Jemalloc is one of them. I don't know if that's the standard, but it's definitely becoming the standard of a lot of different systems. So you have to consult whatever your libc is, whatever malloc it uses. But yeah, you can just the shims are already provided for you.
Mm-hmm. So which allocators don't have the fixed size problem?
So most allocators don't have a fixed size problem. The fixed buffer allocator is the one that is fixed. And it really depends on sort of the strategy that you're providing. Recognizing that having a fixed size is probably not the best approach. Most allocators will not have a fixed size. The reason that fixed buffer allocator is fixed is because it's simple and it's fast. Those are two very good qualities that you want. And if you're able to make the trade-off there, that's why you want. If you don't care about expanding memory, you should almost always want to use fixed buffer because it's just faster. Mm-hmm. But if you need any sort of expanding memory or you need a free memory, then that's when you want to venture out and use a different one. So there's only one that's really fixed because there's no reason to use a fixed buffer allocator otherwise, because the fixed buffer allocator is probably the fastest that you'll ever get.
Yeah, I remember using the fixed buffer allocator a bunch of times, I think while I was writing tests for my Redis client library. And so since I was controlling the input, I knew how much memory I needed, and this was really the fastest way of having, like, writing the test, making it work, and also have the tests run fast. So that's maybe a bit of a peculiar use case, but that's one that fits well. So there is another question that I think Timmy wanted everybody to answer, but I'm going to pose it to you so that also you can have an opportunity of contributing. And he's asking, why is something like jmalloc considered very fast even while being a general purpose allocator? Is the speed relative or something else?
I mean, the speed is always going to be relative. Using gmalloc will never be as fast as using a specific one for a specific algorithm. So you can always tune whatever algorithm you have to have a faster characteristic. However, for being a general purpose allocator, gmalloc is very fast. And you almost want to use gmalloc as the backing allocator for a lot of different things. Like for instance, if you're allocating dozens of linked list nodes, it's probably faster to pre-allocate that at once instead of allocating each individual one. And to do that, you'll just allocate an array of 24 of these nodes, and that's one allocation call. And that's guaranteed to be fast on almost any system. If you allocate one at a time, it's probably going to be slower, but it's going to be a lot less slower on something like gmalloc as opposed to something like the free list one that I built myself, which is horrendous. So yes, there are trade-offs, and yes, gmalloc isn't ideal for probably any specific problem, but it's good enough for almost every problem, and that's why it's used so heavily. And generally, you want a general purpose algorithm that makes these trade-offs and has like 90% performance for almost every non-degenerate case you can throw at it. And that's what makes it general purpose. It's never going to be great. It's never going to be the best. And it's never going to be perfect. But it may be good enough that it doesn't matter.
Mm-hmm. So there's a comment from Andrew related to jmalloc, where he says that he would be interested in seeing a port of the entire library rather than trying to use it directly.
Yeah, that's a possibility. jmalloc is non-trivial. Looking at the code size of that, it's pretty big, and there's a lot of different concepts going on. I mean, it's a project of like decades of experience. Most of the concepts I presented is just one or two of them. jmalloc probably uses like a dozen or 24 different strategies that actually works together. So yes, that's definitely something that we would like to do, but it's also probably very complicated and might take a full-time staff to work on properly, at least to get it off the road. So it's possible, but it's complicated for a good reason. And also, because it's so complicated, I refuse to use it in WebAssembly because I think the output size of jmalloc was like 500 kilobytes. And that's a little bit ridiculous. So I don't personally use it because I write a lot of stuff in WebAssembly, and forcing to download 0.5 megabyte of binary is just a little bit ridiculous. So again, trade-offs. It's fast. It's pretty performant. It takes a lot of binary space for it to actually work.
So this is a question from me. I remember reading recently that there was a new allocator strategy that there was a research paper that I think made the news a while ago, where they were adopting a strategy where they would try to allocate let's say that you have two pages. They would try to allocate non-overlapping areas of memory of the two pages, and then they would be able to merge the two pages together, right? Have you had any experience with that or opinions?
I've watched the talk on it, and it's interesting. The thing that they're doing is that when you allocate arbitrary memory, it's very easy for your memory to be fragmented to hell. And one of the strategies to how to defragment this is by merging pages. If you have two different pages and they don't have overlapping used memory, most operating system allows you to just glue the two pages together. They still look like they're separate, but underneath the covers in a virtual page memory thing, it's actually one continuous block of memory. And this allows you to merge pages and reclaim a lot of the fragmentation. I don't know how any of that works. I don't really work with operating systems. This requires a lot of in-depth knowledge of how each individual operating system works with these pages and how to actually merge them together. Their solution is literally to just randomize which page it's on, and that works better than like 90% of every other solution, including linear scan. So somehow randomizing the data makes the random fragments easier to compress. So it's interesting. It sounds impressive. I don't know much beyond just the video that I saw.
Okay. So the questions are getting harder. So I think I will conclude with another hard question. Well, it's not precisely a question, but it's a discussion that's going on the IRC channel on Freenode. And I don't know, maybe you had an opinion on that. So there's ACE-CVE on IRC that is asking, just curious, but would it be possible to make a garbage collecting allocator?
I think the answer is yes. I've actually seen one written by Jimmy. It was pretty old, and this was before I really understood memory allocation. So it looks like it's possible. I don't really know how it works because traditional garbage collectors require tracing, and we don't actually have a good way of tracing memory usage in our metadata space. Or like most manually managed memory spaces don't have a good way of tracing. I mean, it's possible we could build like a pseudo graph on top of that, but I don't really know how it works. But because one was written already, I'm inclined to say probably it's possible.
Okay, so some food for thought for the people watching. Well, that was awesome. Thank you, Benjamin. Is there anything else you want to say before we move to the break?
No, I think that was it.
Okay,
Thank
then
you very much.
I will say it for you. Make sure to check out his Twitch channel. That's twitch.tv/FengB. Is that correct?
Yes.
So make sure to watch and to ask him questions about memory allocation, WebAssembly, Game Boy emulators, and stuff like that. So thank you very much, Benjamin, again.
Thank you.
Okay, so now we are moving to the break, and 10 minutes, but don't go away, because when we come back, Andrew is speaking about the Zig compiler. So see you. Andrew Kelley used to work at OkCupid. One day, he was put in front of a big C++ code base, and rather than work on it, he decided on the far easier path of leaving the job to design and implement his own programming language from scratch, surviving on donations. The talk is titled Zig Compiler Internals. Andrew, the stream is yours.
Ooh, sorry, I just wasn't expecting the joke to be that good. Hey everybody, welcome to Zig Showtime. Thank you, Loris, for hosting. You're doing an amazing job as usual. And thank you also to Benjamin. That was an excellent talk. I love how Benjamin is always like, well, I don't know anything about allocators, and then just comes out with this content. Oh man. Okay, so here we are. We're going to talk about Zig compiler internals. Shout outs to King Prati for this picture. Let's get started. So all compilers are pretty much the same thing, and the Zig compiler is no exception. So, I mean, this is really what there is to it. The first thing you got to do, you got to take the programmer's source code, and you need to tokenize it. And this is so simple. All you do is you iterate over each character, and you figure out, is it part of a string literal? Is it part of an integer literal? Is it, like a plus sign, something like this? This is called tokenization. So this is so simple. You can do it with a regular expression, or you can write, a for loop with switch statements and sort of hand code your state machine. And what you end up with is a list of tokens. So that takes you to the next step. The next thing you got to do is take your list of tokens and you want to parse that into an abstract syntax tree. And so this is the part where you say, okay, I see a bunch of tokens here. Is that an if statement, or is that a function call, or is that a function declaration, or is it a parameter? So you've got to take your tokens and turn it into the actual understanding of the language. There's a lot of tools to do this. Tools like Flex and Bison are called a parser generator, and this will do the tokenization and parsing for you, and you can sort of just declaratively describe your syntax, and they'll automatically generate the code for you. Or you can write a recursive descent compiler yourself that can help you do error recovery better. It can help you give better error messages. Or if you're an absolute madman like Kamari Spaghetti, you can write a handwritten, non-recursive stack-based parser. And if you want to hear more about that story, ask me in the QA. It's a pretty funny story. Okay, so the end of this part of the pipeline, we're going to have a tree of AST nodes. And we need to take that, and we're going to generate some sort of intermediate representation. And this looks slightly different in different languages, but it's all the same concept. In Java and C Python, we have bytecode that is this part of the pipeline. In the Clang C compiler, this is LLVMIR. In GCC, this is the Gimple. Every language has this. And then finally, we need to take that those sort of virtual machine IR instructions, and now we have to actually figure out, okay, what are we going to tell the CPU though? And this is a part where you actually have to care what CPU you have, because a RISC-V CPU and x86-64 CPU do not understand the same instructions encodings, and they certainly don't understand your imaginary IR instructions. So you have to give them actual concrete machine code. All right. And this is really it. But you could add a few more steps into the pipeline. So, for example, in between those two steps of the IR and machine code, we might add some optimization passes in. And in this part of the pipeline, we're going to start and end with the same thing. So we start with a bunch of IR instructions, and we're going to end with a bunch of IR instructions. But hopefully what we're going to do is we're going to change it so that those new set of IR instructions are more efficient. And maybe we're going to delete some dead code. Maybe we're going to promote some memory access to registers, that sort of thing. And then finally, once we are done with the optimization passes, hopefully we have better IR instructions. And then finally, what that actually produces is an object file. And then in order to run the object file, we need to link it into an executable. So there's the whole story. Now, let's talk about Zig specifically. In Zig, it's the same thing. This is the same thing that we were just looking at. But just to be more specific, the intermediate representation is broken into two parts. So the first part, when we take the AST nodes, we're actually going to generate untyped Zig IR instructions. So these instructions encode a control flow, but they don't have types yet. And then we're going to do a semantic analysis pass. And this is the big part of the compiler. There's a file in the source code called ir.cpp that does this box over here, the semantic analysis pass. And it's 31,000 lines of code. And it's all just that box right there, semantic analysis pass. So that's the big one. And what this one does is it's going to take the untyped Zig IR instructions, it's going to iterate over them, and it's going to evaluate all the instructions and find out, do we know the value at compile time? Can we do the control flow at compile time? And if yes, then it does it. And if no, then it's going to emit runtime control flow and runtime instructions. And then finally, since
Sorry, Andrew.
Zig uses...
Sorry to interrupt you. I think your desktop went black.
Oh, no.
Can you double check?
Yes.
No worries. That's the beauty of having me here, so we can diagnose this stuff immediately.
Yeah. It seems to be working. Should I refresh the Laplace?
Okay, let me then double check that it's not on my side.
Oh, I just exposed the room as well, by the way.
Don't worry, we are not seeing anything. And let me give me a second. So here's what I'm gonna do. I'm transitioning to a logo, so people don't see anything. Don't worry. Now let's diagnose what's happening here. Okay, I can try to refresh page. Okay, I think it's working. So you know what? Might even be my fault. I apologize for that.
Oh, no worries.
Yeah, you can.
Tell me when.
You can switch back to your view, and I'll transition back.
Okay. So everyone heard my audio, is that right?
Yeah, it's just the video that stopped.
Okay.
You can start.
Okay. Sorry for the hiccup, everybody. So anyway, we're looking at the big box on the bottom right, and we're going to take the untyped instructions. We're going to do compile time known things at right now, and then if anything that we can't do at compile time, we're going to emit new Zig IR instructions, and this time they have types. And then finally, because Zig is using LLVM, instead of Zig making machine code, we actually just change the Zig IR instructions into LLVM IR instructions, and then the Dragon takes it from there. And now what I've just described here is stage 1. So I put the familiar GitHub label on the top right there. You've probably seen that on issues. And if whenever you see that label, you're probably also used to seeing this label next to it. So I'll just put that up right there too. That's just a joke. But anyway, that's the process for stage 1. And I know that it's not always, if you're in the IRC channel or the Discord or whatever, we're throwing around these words: stage 1, stage 0, stage 2, all these things. So I want to tell you what's going on with that. So that's how the compiler works from a code perspective. Here's how we build it. And like, what are the stages? So the first thing that we're going to do here is we're going to take all this C++ code, and the C++ code implements Zig, right? Because before we have Zig, we can't write Zig in Zig. And what we do is we compile all of the C++ code into a static library called libzigcompiler.a, and we then also throw in one more C++ file into that, and that's going to create Zig 0. So that's actually stage 0, not stage 1. So once we have that, we have a Zig compiler. We can compile Zig, but it's missing a lot of features. All the things we're used to having: Zig format, Zig CC, translate C, all these things. You can't do them with zig0.exe, and that's because that stage2.cpp file, it's a shim. It just contains a bunch of code that says, oh, if you try to do Zig format, crash, panic. If you try to do translate C, crash. I don't know how to do that. I'm just a shim. All these things with the red X's will just crash if you try to do it with zig0.exe. But it can compile Zig code as long as you don't use these features. So what we do is we take zig0.exe, and we then use that to compile some code from the self-hosted compiler. And the sort of main file that is here is the stage2.zig file. And now look at what we're doing here. We're taking the same libzigcompiler.a, except instead of stage2.cpp, we're using stage2.zig. And we combine these together, we link these together into zig.exe. And that becomes stage 1. And now we have all these features that we didn't have before. So now we can do Zig format, we can do translate C, Zig CC, all these things. So that's how you get from stage 0 to stage 1. And the beauty of this is that all that .zig code, that is code from the self-hosted compiler. So we're actually sharing code from self-hosted compiler, even though it's not, even though we're not fully self-hosted yet. Okay, so what do we do next? What's stage 2? Well, I just moved everything over to the top left here. So once we have stage 1, now we're going to take all of the Zig self-hosted compiler code. You can see some of these files are the same, but there's also more there. And now we don't need the glue code of stage2.zig anymore. That was just the glue code to put it into the other compiler library. So now we're going to actually compile all the stage 2 code, and finally we end up with the self-hosted compiler. And that's where, and you can do this right now, but it's not done yet. Like you've probably seen some of my demos where it can compile like some hello world stuff, but it's not ready to go. We can't ship it yet. So actually, we're still shipping stage 1. If you go to ziglang.org/download, this is what you're getting stage 1. All right. So hopefully that gives you an idea of the build process and how this stuff works. Now this is the part where I'm going to show you a demo. So let's go over the same sort of pipeline in stage 1, and I'm just going to give you like a tour of the code. So if you're curious or you want to contribute or you just want to kind of know your way around stage 1. Now this is where I'm going to show you where everything is. Okay, so the first thing we do is tokenize, and now I'm going to tab over to my Vim here. So the tokenization code in stage 1, it's in this tokenizer file here. And let's look at the data structures as well. So all we're going to do here is turn source code into a list of tokens. So the main thing here is this enum, and you can see the enum has everything like a bang, or has all the keywords in it, and it has like a string literal. So this is all the different tokens, and there is some a little bit of extra code here for special stuff. It's also using a lot of memory per token, which could probably be improved. But anyway, point being, the thing we're going to end up with is this list of tokens. So in order to do this, this is a hand-coded tokenizer. Got to list our keywords here, and we have essentially a state machine. So this is an enum of states, and then the main tokenized loop is going to look it's going to look like a very certain pattern. So here it is, the main tokenized loop. We loop over the source code, switch on the state, switch on the character, and then we either emit a token or switch states, and that's it. That's the whole thing that a tokenizer does. So I'm going to sort of scroll through here, and you can just sort of see the structure is really consistent, right? Switch on the state, switch on the character, emit a token, or switch states. That's really all there is to it. It's really easy to debug. It's easy to add stuff to, and we end up with a list of tokens. So that's it. That's the tokenizer. Next, now we have a list of tokens, and we need to create a tree of nodes. We need to actually understand the syntax. So that's going to be in the parser code here. And the type that we're going to end up with is this AST node struct. Now, again here, I'm using a union for all the different types of AST nodes, which again is pretty wasteful of memory. That could be improved. But I mean, it gets the job done. So what we need to do is create these nodes, and each one of these nodes might link to other nodes. It's a tree structure. So that's what we need to end up with. And so what this is going to look like is this is a hand-coded recursive descent parser. There it is. And And so what it's going to look like is we have a bunch of functions, and we're going to, it looks a lot like the grammar definition. So here we're calling parse container members, and you can see that the functions sort of have this text in front of them that gives you an idea of what it's supposed to do. So we're looking for a test decal, or we're looking for this, or we're looking for this, or this, or this. And so you can see we try looking for a test declaration, we try looking for a top level comp time, we try looking for a top level declaration, and at the end, what we're going to do here is we're going to emit an AST node. So you can find, I think it's like AST create node. Yeah, this function is going to be called everywhere here. We're just creating these nodes, we're hooking them up, we're returning them, we end up with a tree. So next, we need to take these AST nodes and we need to generate our untyped Zig IR instructions. Okay, so the types for this is here. It's IR, it's circ. There it is. So this is sort of like the base struct for this thing that we're going to generate here. Now, let's go look at this enum here. So these are the types of untyped IR instructions that we can emit. So you can see there's declaring a variable, there's a branch, conditional branch, switch branch, there's a binary operator, a unary operator, you can load a pointer, unreachables here. So this is where we flatten out the AST into a set of instructions. And what this flattening can do is it can turn, for example, a while loop and a for loop into basically the same structure, so that you don't have to code you don't have to write the compiler code for a while loop and a for loop twice, because these can just emit instructions, and then you know how to operate on the instructions. So where this happens is in this function called, it's in ir.cpp, this monster file that it has 32,000 lines in it. I think it's AST gen node raw. There it is. Okay, so this is sort of like the main function here, and you can see that we're switching on the AST node type. So if we see a block, we call this function. If we see a binary operator, if we see a string literal, that sort of thing. So let's look at a really simple one. Let's look at a string literal or integer literal. There. So we're looking at this part here for an integer literal. So here we have a node that is an integer literal. It's super simple. We don't have to do any logic. All we do is we create an instruction which is a constant, and the AST node has the big int value of the integer literal, and now we just have a constant instruction which represents this value. That's the simplest possible one. Now let's look at a slightly more complicated one. So we're going to look at I think let's look at a unary operator. Which one am I looking for here? Anyway, let's look at a binary operator because I didn't find the one I was looking for. So we have assignment operators. Let's look for like add. Okay, so here's one. So here, yeah, this is a good example. So here we're doing a binary operator. And you can see we're recursively calling IR generate node. And so again, this is the part where it's turning AST nodes into instructions. So we get an instruction for the left-hand side of like the add, for example. We get an instruction for the right-hand side of the add, and then we emit a binary operator with these two instructions. So pretty simple. So once we're done with that, this is where all the magic happens. So now we have a set of untyped Zig IR instructions, and we need to do comp time evaluation, comp time control flow, and then emit runtime instructions. So all of this happens in this function called IR analyze. And there's there's a bunch of debug stuff here, but the main loop is here, where we're iterating over the old IR instructions, and the main thing here is right here. So here we're passing in the untyped Zig IR instruction. We're calling IR analyze instruction. We're getting the new instruction. This is the single line right here. It represents this transition right here. And so if I go into this function, again, you can see we're switching on the type of the untyped instruction, and now we're doing the analysis. So I think the one I wanted to show you was bool not. Yeah. So let's look at the analysis for Boolean not here. So this is what this part looks like for a Boolean not operation. So the first thing we're going to do is just get the operand. We're going to get a handle to the Boolean type. Then we're going to cast the operand to the Boolean type. And this code right here is the part that will give you a compile error if you tried to do a Boolean not operation on, like an integer or a string literal or something. This is the part where it would tell you like expected Boolean, but found something else. If you delete this code, then you'll get a compiler crash instead of a compile error. And then finally, this is the part where we're doing compile time stuff. So this pattern is good. This is a representative pattern of how this works in all of the compiler. So all we're going to do is we're going to check if the operand is compile time known. If it is, we get the value, the compile time known value. And in this case, we're going to emit a constant.
Andrew, sorry to stop you again.
Mhm.
I think the video broke down pretty bad in the last like 30 seconds or something.
Okay.
So I think people were stuck seeing the bool type example.
Okay.
Can we try to redo the? Can you try to share me another link?
Yes.
Sorry, there have been a couple of hiccups also during the presentation, but I've been restarting the stream like very fast, so I didn't want to interrupt you. But I think that we're probably far apart. So for the people watching, Andrew is closer to the West Coast in the United States. I'm in Europe, so it hasn't been a problem up until this day, but that's what you get when your whole network is best effort.
Let me know if we're good. I sent you a new link on Discord.
Let's see. Yeah, it's loading really, really slowly. So, what if you try to enable screen sharing on Discord? I think we can make this work.
Yep, on it. Okay. Wait, why does it say go live?
That also works, but you have a share your screen button. You should have it on the right side next to the video button.
Okay, I click it.
Sorry, everyone. We're going off stream with the audio for a moment so that we can fix this. Be right back. Okay, I think we can resume.
Okay, am I live?
Yeah, you're live.
Okay, great. Thanks everyone for your patience. Don't worry, I anticipated this, and I put a little picture in the bottom left here for you, so you can see what I look like. Right, so we're in the middle of talking about this part of the pipeline, and I'm showing you what a Boolean not looks like, right? So if you do the bang on a true or a false. Okay, so we went over that this is a part where it does type coercion. So this is a part where it gives you compile error if you try to do a not on a non-Boolean. Finally, this is the heart of how comp time works. So it's actually pretty straightforward if you think about it. So we check the value. If we know the value at compile time, we know that it's true or false at compile time, then we just get the value. And we just do the Boolean not right now. So right here, there you can see we're doing it. And we just emit a constant instruction rather than adding the instruction to the list. Now, if that doesn't happen, if we don't have the operand as a comp time known value, then we go on to this part. And this is where we actually emit a runtime instruction for the next part of the pipeline. Right here, we're adding the emitting a runtime instruction. So that's it. That's how this part works. And what we end up with is now all of the stuff that could be figured out at compile time is done. It's gone. And the stuff that's left over, the stuff that we only know at runtime, makes it to the next stage. So now we're on to this part where we render the typed Zig IR instructions into LLVM IR instructions. Now that happens over here at CodeGen. And this function's kind of long. We got to do a bunch of stuff, but basically at the end here, we're going to be calling IR render. So this is the part where we're doing this for each function. So now we're going to iterate over the Zig IR instructions. Sometimes we can skip them. But again, we have this one line here, which is sort of the heart of the issue. This one line represents this just transition here. So here, again, we're having a switch on the Zig IR instruction type, and we're going to do something different depending on which one it is. And so let's go find our example again, our bool not. So in the case that we had to emit a runtime instruction, we can see what we're doing here. Where actually LLVM doesn't have a Boolean not, but it has integer comparisons. And the way that we represent Booleans to LLVM is with an I1. So this value is going to be an I1 because it's a Boolean. And then what we do is we take the value 0 and we say if the operand equals 0, that's our result, right? Because 0 equals 0 will turn into 1, and 0 equals 1 will turn into 0. So it flips the Boolean around. So there we go. And now we have an LLVM IR instruction. We can look at one more interesting example here, unreachable. So if we emit a Zig IR instruction for unreachable, then we're actually going to check, do we want safety on? In this case, we're actually going to emit a crash. Otherwise, we're going to actually emit a LLVM unreachable instruction. So finally, we've given LLVM everything it needs. LLVM takes it from there. It does all the stuff in the back end. And what this is going to leave us with is an object file. So that's gets target machine emit to file. There it is. So this is going to end us with an object file. We're not quite done yet. We have one more thing to do. We need to turn the object file into an executable. And so finally, we have to, depending on the kind of object file, is it a Windows one? Is it an ELF one? Is it the Mac OS one? Or is it a WebAssembly one? We have to basically construct a linker line that we're going to send to, again, LLD, another part of the LLVM project, that will then do our linking for us. And then once this is complete, we have an executable, we can run it. All right, that's it. Now, there's a lot more details here to go into, of course. We might want to talk about self-hosted, stage 2 and how that works and how it's different. It's designed fundamentally differently. We could talk about the cache system, debugging tips. If you have any requests, let me know. I can fill in. I could do more on this sort of like series. If we need to fill in more slots for Showtime. So, however we want to do that, we can do that. And that's it. With that in mind, I think it's time for Q&A.
Yep, thank you. I didn't notice I was muted. So yeah, let's switch to the Q&A. Thank you very much, Andrew. Sorry everyone for the screen sharing issues. I think Laplace has never let us down before. And I don't know, I think we're gonna diagnose this. We did try briefly to make sure it worked, but who knows? Maybe we'll find a solution. But certainly we'll figure it out. An easier, more accessible fallback option in case this happens again. So Andrew, while people start thinking about questions, I think I'm contractually obligated to ask you the first question. I'm sorry. When did you discover Zig, and how did you discover it?
I discovered it in the shower. Yeah. No, actually, I actually could tell you a little story about that. I was working on a digital audio workstation as sort of my big project, and until that point, I'd always just bounced around on little projects, and I was interested in so many things, but I couldn't stick to one project. And so my goal was to pick something really hard, like a digital audio workstation, and just focus on it and actually put a lot of time into it and make it into a big project that it's, worthwhile and actually, accumulates, some critical mass and that sort of thing. And I was doing pretty good on that, but I actually went through a breakup at the time that was kind of hard, and I thought, oh, I need to just relax and have some fun. So I started working on a programming language instead of the thing I was supposed to be working on. And oh man, a programming language is so much easier than a digital audio workstation. It was just such a joy, so that's how it started, and then I just didn't stop.
I see. So, so you're basically, this is a big parenthesis, but you know that once you're done with the language, you will have to go back to that then.
Yep.
I see. I see. So, I have another question for you. So you mentioned that all languages go from an AST to IR, and then to machine code. So what prevents compilers from going directly from AST to machine code? What does the ER provide in the middle?
That's a good question. So nothing really. You could do it, but you'll find yourself duplicating a lot of things. So as an example, if you have a while loop and a for loop, and other languages have a lot more syntax, so maybe they have 2, 3, 4, 5 different ways of looping. If you do it with an AST, you're going to find yourself writing code that's very repetitive and duplicated for each of these different constructs, and in a way that's very hard to abstract. It's very hard to dry up your code, and also, so if you do the IR, then you end up having all of those syntactical constructs take the same path, which is easier to maintain. Finally, if you want to do any kind of optimization, doing optimization on an AST is a nightmare. It's just, I mean, it's I think that's what they have programmers doing in hell, is trying to do optimizations based on an AST rather than like a intermediate representation. I don't even know how to explain how much of a pain it is. I think in my college course we tried to do optimizations on an AST, and it's just not feasible.
I see. Okay, I see there are some questions piling up. Second question, in case somebody else wants to add their question. So I remember watching a while ago a video by Rob Pike, who was on stage and was presenting a detail about the Go compiler, where he was making a great point of the fact that the Go compiler had a intermediate stage before generating machine-specific code that was shared by all, let's say, architecture-specific backends. Did you watch that video?
Yeah, I'm familiar with that. That's specifically for the Go assembly language abstraction layer. Is that right?
Yeah, I think so. So how does that relate to what you showed us?
How does it relate? Oh, okay. So in the pipeline, that would be.
I can put your screen back on the
No,
screen.
don't worry about that.
Okay.
It doesn't actually go. Wait, I'm trying to remember. Is that part of their code generation, or is that just part of their assembly pipeline? Yes, it's part of their code generation. So, actually, yeah. Can you put my screen back on?
Sure. I think you need to share it again, though.
Oh, right, of course. Thank you for reminding me. Oops. Okay, are we looking at my screen?
No. Give me a second. I don't see your screen share. I think can you try again?
Yeah.
I mean, I can see myself without the webcam. Okay, now it works.
That works?
Yeah.
Okay. Right, so this is the whole pipeline here. And the way that Go has their setup, they have an additional box right here in between render IR instructions and the machine code instructions. And yeah, this box here is split into two. So what they're going to do is they are going to have this step, but instead of rendering IR instructions directly into machine code instructions, they have another layer where they render it into like a second IR layer that is basically just machine code abstracted across architectures. So that's how they do it.
I see. Because because the IR is designed by you, right? Your IR is whatever you want it to be, right? While these assembly, the Go assembly is much more closer to what the general parts of that all architecture share.
Yeah, that's right. So what Go has done is created a virtual machine that very closely resembles a virtual machine that's designed to be as close to all of the actual machines as possible, yet still abstracting across them. And so then they target that layer, and then what that does is it just makes it very easy to add another actual machine that comes out of that layer.
Right. Do you see this being something useful for the Zig project, in your opinion? Something that you would want to investigate in the future?
I actually put a little bit of thought into this, and after I watched that video, I think that there is a specific reason that Zig's design goals are different than Go's. That means that we should not do that. I think that if your goal is to support only the most popular architectures in the world, then Go's approach makes sense. only if you only want to do x86, ARM, whatever ends up being popular. However, one of Zig's goals is to support even exotic architectures, like a truly general purpose language that can support weird architectures. And in this case, you can see how the abstraction across weird architectures would not quite fit. And in this case, we would need inline assembly that is more specific to exotic architectures. So we have less to gain from this kind of abstraction. So for that reason, I think that this would not be an appropriate layer to add to Zig's compiler design.
I see. Thank you very much for that answer. So let's do a few questions from the audience. First question from Timmy. Did you write any compilers, maybe toy compilers, before Zig? And or what was your first experience writing a compiler?
Yeah, I did one in college. The problem was to create a Pascal sort of language, and the professor wanted us to compile it into C, but that just felt such like cheating to me. So we got the professor to agree to make it so that we had to emit MIPS instead of C, and that was a lot more fun. That was my first compiler project, but here's my actual secret. I said we because I did the project with my good friend and roommate from college. His name is Josh. And Josh has written a lot of compilers, and he was very involved in the early design decisions of Zig, and still involved today. I still call him up on the phone and talk over a lot of the issues with him. So that's my real secret. I just have a friend who's really good at this stuff, and then just will talk to me on the phone about it.
I like this strategy, by the way. Yeah, having other people do stuff for you, it's amazing. Yeah. Another question from Suirad. Are you excited to rewrite everything in Zig?
Oh, super excited. I've started. You can check out what we have so far in self-hosted, and it's so nice. I mean, it's a nice piece of software. It's already extremely fast. I mean, it doesn't support a lot of the language because it's not done yet. But the thing is, if we can just if it just keeps the speed it's at now, it's going to be incredible. All we have to do is not slow it down from what it's already at. If we could just add more of the language without making it worse, it's going to be great. And I mean, the incremental compilation is working. The design is good. The way that it emits machine code instructions is working fine. We're even set up. I didn't realize this at the time, but with the way that incremental compilation is set up, it's actually just not that much more work to add hot code swapping. Actually, really robust hot code swapping. So yeah, I mean, it's great. The coding in Zig is great. It's a good language, and so the project is really exciting. My only sadness is that I just can't go any faster. I'm just doing a lot of the hard design decisions up front at the beginning, and progress just feels really slow. But I'm convinced that it will pay off to invest in these difficult design decisions up front.
Another question. This is from Luna. What about the non-recursive stack-based parser that you mentioned earlier?
Nice. Yes. So if you've been following along with the recursion story in Zig, then you will know that we now have a plan so that, a recursion plan where you can't just do naive recursion. You're going to have to sort of do some stuff to heap allocate the recursive frames. Or anyway, point is, you're not going to be able to do normal recursion, but we have a plan so that you can express your code just recursively still. That didn't used to be the case. It actually used to be the case that we just thought we weren't going to be allowed to use recursion in Zig at all. So as sort of a proof of concept, I sort of started doing the self-hosted parser in a without using recursion at all, right? Like I'm talking about writing a recursive descent parser without recursion, using like a stack and just creating all these like structs and stuff. And I just like did a little bit of work on it, and I was like, okay, I think this might work. And then I just went on to like work on other stuff. And then Komari came along and finished it, like just did all the work and wrote the whole self-hosted compiler with no recursion. And two things. One, quite frankly, it was just like a difficult code base to maintain. Like recursion is useful. It's a nice way to express recursive concepts. So it was like it was kind of annoying to maintain the code because you had to like think about it in a really weird like stack-based way with like structs and types and all these things. It was almost like a whole like language you had to learn to write the parser. Okay, but two, the fact that Jimmy did that, I mean, Komari did that was incredible. Like so much respect for pulling that off. And it was almost sad when we had to, retire the code and favor the more maintainable recursive version. And that work was done by Stevie Hershew. But don't worry, because we have the pull request where it happened, and there's a lot of like rose emojis and like gravestone emojis and stuff. So, there's a nice little like grave site for the old code.
So you gave it proper burial.
Yeah, proper burial. Yeah.
I see. Okay, let's see other questions. What part of the compiler most gave you headaches?
Yes. That could be an entire future topic, and it's the part where result location semantics, compile time semantics, inferred variable types, and inferred pure type resolution and inferred comp time all in the same expression. That code just doesn't really work, and you're going to hit compiler bugs, and it's not really fixable. The design of stage 1 is not really at a place where that can be solved. It's just a disaster. If all those 5 things combine at the same time, there's no plan for that in stage 1. It just doesn't work.
You need a better language to handle the stuff, right?
Yeah, exactly.
So how did you check the Zig grammar? Timmy says, I often find myself struggling to fully understand and or eliminate left recursion, etc. Do you actually remember all the theory from uni?
Oh, no, I don't remember any of that stuff. I just had a lot of help from the community. So Komari actually wrote someone could probably drop a link in the Twitch, but there's a Zig spec repo, and it has a parser expression generator definition for the Zig language. And so you can use that to you can use that as a formal specification. Komari just did that. So that's really helpful. Earlier on, when I was doing a lot of syntax stuff, I would call up my buddy Josh, or we were roommates actually. So I would just go into the living room and I would say, hey, I need to change the syntax of Zig, and here's my idea. And he'd be like, no, you can't do that. I'm like, why not? And he would explain like all these things. And then I would say, oh, okay, well, what about this? And he'd be like, no, you can't do that either. And like, finally, we would just get to a point where he goes, yeah, that'll work. You can do that. And I was like, okay, thanks. Honestly, that's how the syntax evolved of Zig.
So Benjamin asks, why did Zig use the percentage operator, and why was it removed?
Yeah, why did I do that? Yeah, I don't know. I think earlier on I was there's sort of 2 things you have to work on at the same time. You have to work on the syntax, which is like the clothes that you're wearing, and you have to work on the semantics, which is like what does the robot body look like? That's a weird analogy. Anyway, point is, there are 2 sort of like completely orthogonal problems where like one is how something looks and the other is how it functions. And I mean, you can just work on these problems independently. And so for a lot of situations, like it's easier to just focus on one and worry about the other one later. So double percent was a good example of that, where I just needed some syntax so that I could test out these semantics I wanted to test out. And I didn't don't know. I didn't really want to get locked into or like I didn't have the brain power to solve two of these different problems at the same time. So I figured out how the semantics should work, and I felt good about it. And then later, I realized that the parentheses were just too ugly for people to even like pay attention to the language at all. And so keywords. And also, we made it so that all control flow happens exclusively via keywords, and that was a good decision. And in retrospect, like I'm also happier with the way that the syntax evolved. So, I don't know. To summarize, earlier on, I focused a lot on semantics, and then for me, like the syntactic choices just take a lot of like time to sleep on it and just get some input from a lot of different people, and then finally you pick something that hopefully doesn't have to change.
You also answered, I guess, partially the next question. So I'm gonna ask you the second half, which you didn't address specifically. So, is maintaining a syntax close to C, C++ an important design choice for Zig?
I didn't. I'm not sure it's explicitly uh, the reasoning behind it. I guess what the alternatives are would be like a Lisp sort of syntax, or I don't know, a more exotic one. Um, I do think that there is a lot of value in having people who know programming languages but not the Zig programming language be able to look at Zig code and already be able to read it without looking up any documentation. I actually think that that's a big deal. Like I think that I think the familiarity does matter. But ultimately, I just want syntax that's easy for humans and easy for computers to parse both. That's the main sort of actual drive.
So last two questions. Let me do the second one first, then I'll finish with the other one, Timmy. So I'm not skipping one. I'm coming back to that later. So how did you get started with the LLVM part? The documentation seems extremely terrible. Did you power through, check the toy language example in the site? Do you have prior experience? How did you feel about that bit?
Yeah, that's a good question. So the documentation for the LLVM IR is actually pretty good. There's like a langref.html file, and it's quite extensive. It explains all the instructions, all that stuff. It's pretty good. As for the actual API, yeah, you basically have to read the source code in order to use it. But yeah, I mean, I think that I was just so fascinated by this how powerful this API was, especially before I got into doing any compilers, that it was just it was interesting enough, that it made me want to play with it. I did the project. If anyone remembers, like a few years ago, I think I called it Jamulator, statically recompiling NES ROMs into native executables. That was sort of my like first foray into using LLVM and Clang and stuff, and I had a fun time with it. So from that point, I realized that was sort of a library that I could use for code gen if I wanted to.
Okay, final question from Twitch chat. Still from Timmy. I recall a plan for a non-LLVM backend for Zig. Does that mean that Zig would generate assembly for all supported targets?
Yes, not assembly though, machine code. Assembly would be the human readable version of machine code, but we don't even have to do that. We can just skip that step straight to machine code. And in fact, that is what the self-hosted compiler right now, as it stands, does not have an LLVM backend. It is only a purely self-hosted backend. And the plan is to make LLVM an optional dependency. Right now, it's not even a dependency at all. So when you use a self-hosted compiler, Zig takes your Zig code, does some analysis, and then it's going directly into the binary file. That's why it's so fast. So the plan, the grand plan for the future is that LLVM gets tacked on as an optional dependency, and so there will be a fast debug backend. The point is just we want to compile fast, and then when you want to go into release mode, that's when the optional LLVM dependency would be useful, because now you go through LLVM, you get all those optimizations. You're willing to wait the extra time for that release build, and then we have the best of both worlds. But yes, the answer is yes. It does depend on writing architecture-specific code for every architecture that you want to support.
Okay, awesome. So I guess we can conclude with one final question from me, which is not really a question actually, but I think I think this is a good opportunity to inform everybody of what's going on. So why don't you tell something about the next Showtime episode? Why are there no speakers?
Yes. Okay, so next week, no Showtime. Next week after that is going to be a special episode, and we're going to have some long-awaited announcements regarding the Zig Software Foundation, and I think it'll be worth attending.
Whoa.
That's all I got.
Yeah. So yeah, it's gonna be interesting. It's gonna be more interactive than usual. We also made sure for once to give something back to the poor people in Australia, so that they can also join one episode, which I think is going to be probably the most important one up until today, so that they don't feel excluded. Even though I do still think that they should apply to speak. That's the right way to get Showtime in your time zone.
That's a good point.
Yeah, but it's gonna be awesome. If you can be there, you want to be there, I assure you. That said, we still have a lot of work to do for that episode to happen. So that's why it's gonna be 2 weeks. Well, thank you very much, Andrew. Is there anything else that you want to say before we close?
Take care, everybody.
Awesome. So let's switch directly to the end scene from here.
So